information about the book. For the book, I have there's a link I put, but this link just for you to log in to do your homework, okay? Not for registration. For registration, Çağlayan Kitabevi is going to provide a link for us. And I'm waiting for this link. And when the link comes, I'm going to share it with you. And you're going to purchase it. There are two versions. You can have this, I'm sorry, there's a course, there are two information that you would need. The course name, Math 101 Calculus Fall 2020. And course ID is this ID that you're going to use when you're registering. And you're going to need a credit card, and you're going to need your student ID number, because they are going to ask you to enter it. Okay, and another information is there are two versions of purchasing this book. One costs $180. It's gonna have the hard copy, MyLab, and with e-text. And second option is MyLab with e-text. It's 150 Turkish lira. Even if you fail the class, you will be able to use this till you pass. They should have something like that option. I will check it out, okay? So it's not just for a short time for this amount of money. Okay, let me check the questions if there are any questions here. Okay, I think it's clear. Now I'm going to Emir, you have a question, please speak.
Hello, teacher.
Good morning.
Good morning, first of all. Yesterday, me and my friends searched the web and found a book for the math. I want to ask that PDF is right, and if we can use it.
Actually, you can send it to me, and I can check it out. I mean, even the previous versions could be okay for PDF.
It is 217 year of 217. It's Pearson's Calculus, Thomas.
What is the edition? I mean, we need
14th.
the edition. Now, 14th is good.
Okay.
Okay, so that's okay, but you would need MyLab, okay, to purchase. So you're gonna purchase anyways, but you wouldn't need to purchase the hard copy then.
Okay, thank you.
All right. Okay, any other questions? Okay, no questions. Let's new messages, probably. Okay. Ömer Faruk is saying, I have a book from my brother. Wouldn't it be a problem? Ömer Faruk, the book we used with your brother was Stewart's book. We changed the book because they have better online resource. Homework and tests are given a lot easier on Pearson's book we are using. I mean, you can use it. The topics are okay. I mean, you can use Stewart's book to learn. However, you are going to use the e-text and MyLab online. You're going to purchase the 150 Turkish lira one, okay? Instead of 180. You save 30 Turkish lira from there, okay? Okay, Emir Gümüşya, can you lower your hand, Emir?
Sorry, teacher.
No problem. We both do that. I mean, we all do that. I also sometimes in the meetings I forget Okay. All right, so I'm gonna open up the lecture. All right. Let me see. Yeah. Okay, give me a couple minutes, okay? Okay, I think I got that. All right. So I think we were left, the page we stopped was, I think 14, page 14. And we talked about the increasing, decreasing, I believe. Okay. That's where we left off. I would recommend you to watch, I haven't put them online, but I want you to watch section 3's videos, okay? Section 3's videos, I talked a little bit more about things, so I want you to watch section 3 videos when I put them, okay? I'm gonna put them hopefully tomorrow, because today all day I'm very busy. I will give it a try today. If I put it on today, then you can watch it today. And also the slides that I'm sending you, the lecture slides, I'm going to send the same file, okay? However, each time it is improved. So I would recommend you to download at the end of, I mean, you can download as you receive it, because you're going to receive it at least 3 times, because I have 3 sections and I'm going to send it 3 times. Make sure that the latest copy is the last one of that week, okay? So we have this such a thing, because I'm writing on this file. Each time I write more details, and the videos for this week I would recommend you to watch for the previous classes, of course, section 3's lecture. And then we'll see for this lecture. This is the second part, so you can just give it a try, okay? Just go through especially your video recording, and also section 3, because section 3 is the last section that I teach, and you're gonna have maybe, and we are a little bit ahead of the lecture there. Anyways, just for this week, this is the case, but for coming weeks, you can just watch your own videos, okay? Okay, let's start. So we talked about the absolute value. Absolute value was important, and we talked about the piecewise function. We just talked about this function being decreasing, increasing, and constant, and it was made up of 3 pieces, as you would see here. Okay. And we talked about, as I told you, absolute value function is very important. We will use it over and over, okay? And it's going to be in different shapes, maybe sometimes. For example, instead of y is equal to absolute value of x, we would see it in this form. Let me do that. Let me put a note here. Okay. I'm gonna make it, I'm gonna enlarge it, because I was told that you cannot see it properly. So I'm gonna enlarge it as much as I can, so that you can see it. So for example, we have, okay, for some reason, okay, just a sec. All right, so y is equal to absolute value of, absolute value of x, okay? We have this version, okay? And we know this is a v-shaped function, and we have, this is example, example, and then we have another example for the absolute value function, which is, I'm going to copy this, okay? You can create new functions by using this. Look, okay, this is another function as well. And the pictures actually for y minus, each time, for example, the way we draw the graph of y is equal to absolute value of x, we would draw, okay, draw first y is equal to x, and then afterwards whatever you see below the x-axis, just take the symmetry of that part on top and get the V-shaped, okay? It becomes a broken line, okay? So we have a broken line. V-shaped is a broken line. Can you see that, right? It's a broken line, V-shaped. Okay, there are first y is equal to x. Then, okay, take the symmetry of the negative part of the graph. With respect to x-axis, and then you get the V-shape, right? You just take the symmetry and you get the V-shaped graph. You get the V-shaped graph. Okay, you're going to do similar for this as well. Okay, let me copy this down. Okay, what you're going to do, you're going to first draw y is equal to x minus 2. Okay, you're going to draw the line. And then you're going to take the symmetry of the negative part of the graph with respect to x-axis, and you get a V-shaped graph, but this graph is going to be shifted towards left by 2 units. Okay, the graph you got will be shifted graph of this. Just one sec. Professor is calling me. I need to respond. Okay, just give me a couple minutes. Buyurun hocam, günaydın. Dersteydim ben de hemen. Sorry about that interruption. Sometimes I have to respond, and this was the case, so I had to respond. I don't do that often. Okay, the graph you would get will be the shifted graph of y is equal to x. Y is equal to the absolute value of x to the left by 2 units. Okay, just consider this V-shaped graph. You shifted all of it to the left by 2 units. Okay, and the graph that you're going to get exactly is this graph, the graph of this. So you can actually, what's the idea here? So whatever we have, whatever the function we are given, actually we can get it from the very simple functions we already know. So y is equal to the absolute value of x is a simple function, popular function we used quite often. And we use that function to create another function. For example, this y is equal to absolute value of x minus 2. You can see my screen, right? Can you read it? Can you read my writing?
Yes.
Okay, wonderful. Okay, perfect. That's what I want. I can enlarge it if you need more. Okay. All right. So this is how actually math is going. So you start with the simple functions. You can easily get complicated functions from simple functions like that. Okay. So this is really a nice thing to have. Okay, I just wanted to tell you that. And yesterday we talked about the parabola, and then the parabola we talked about, and we talked about the general form of the parabola, right? We said that in general parabolas are, let me make it bigger for you. Okay, so y is equal to a times x minus h squared plus k. This is the general form of parabolas, and we gave an example. This y is equal to x squared is a simple example for us. And here a is equal to 1, h is equal to 0, and k is equal to 0. And we also have a note here. Let me write that note. Okay. If the a here in front of x minus h squared is positive, the parabola is opening upwards. If a is negative, parabola is opening downwards. We said that. Now I want to give you another example. Let's make it bigger again to get your attention. Okay, so I'm gonna take this function again. Okay, look. Okay, what I'm gonna do, I am going to take this and then I am going to subtract 2 from it, like I did in the previous example. Okay, instead of x, I just write x minus 2. In this case, my a is still 1, h is 2, and k is 0 still. Okay, and how about the graph of this function? Okay, the graph of this function, y is equal to x squared, x minus 2 squared, actually can be obtained. Okay, can be obtained from the graph of y is equal to x squared. Let me make it like that. Okay, y is equal to x squared. And how do we do that? Okay, by just changing x and subtracting 2 from it, this is gonna tell us that we are shifting the graph to the left by 2 units. Okay, the graph of the function y is equal to x squared, okay, is a shifted function, is a shifted graph towards left by 2 units. So this would tell you, when you subtract a number from x, this would tell you that the graph is going to be shifted towards left by that much unit. If you are adding, for example, okay, I'm going to give you another example. On the other hand, okay, the example is I'm going to make it +2. All right. If it is +2, then my h is going to be -2. Yeah. Okay. Be careful about that. And then how about the graph of the new function? It's going to be still parabola opening upwards. It's going to be the same shape. But the graph of the function y is equal to +2 squared can be obtained from the original, the simple parabola that we just learned. All right. By shifting it, again, shifting is a shifted graph towards right this time. Okay, if you're adding if you're adding a number to x, you are just a second. Let me make sure. No, it's just the other way around. I made it wrong. This is towards right. I'm so sorry. This is my bad. This is left. This is the other way around. Okay, this is my bad, and we have to correct the other one too. If you are subtracting, it is shifting towards right by 2 units. If you are adding 2, it is shifting the graph by 2 units towards left. All right, now this is correct. Okay. So I want you to get the idea that these functions are not very difficult. You can create one from the other. You can create the graph of one from the simple ones. Okay, that's why I'm telling you there are some certain functions that you have to keep in mind. What are those simple functions? Line y is equal to x, y is equal to x squared, y is equal to x cubed, and y is equal to 1 over x, y is equal to absolute value of x. Okay, and what else? Yeah, so far it is good. So if you know them, if you know their graphs, and you can create any graph of function you like. Okay, just shifting to the right and to the left. Let me go back and correct. Okay, correct the absolute value, because in the absolute value I said to the left or to the right. Let me see. I don't remember what I said. Not this one. I think this was it. Yeah. Graph to the right. It should be right. Okay, let me correct that.
Bobo.
Go ahead. You have a question? Anybody has a question? Let me check. Okay, there's a chat here. No questions? Can you follow? I mean, does it make sense? Does it make sense for you, what we are doing?
Yes.
Okay. All right, so we did that. So each time we talk, we are going to make it deeper and deeper. So you don't have to learn everything all at once, okay? So we are just writing some notes here and there, and then try to get as much as you can each time. And we are going to get deeper and deeper. The more we talk, it's going to get deeper, and your understanding is going to get deeper, okay? And if there are any parts that you don't understand, you're going to just stop me and ask me questions, okay? That's the deal. Okay, yesterday, actually, in my class, I also talked about the greatest integer, and I remember we didn't talk about that. Did we talk about greatest integer with you? Maybe we did. Do you remember? Anybody remember?
We did.
We did, right?
Yes, we did.
Okay. Thank you for the comment. This is the step function. Okay. And the definition we talked about. And this is, you're going to get like steps like that. Okay. The graph is going to look like that. All right. So let's move on. We talked about the increasing and decreasing function, as I remember. And increasing, decreasing function is what? When you go towards right, if the function is getting bigger and bigger, it is an increasing function. If you go towards right on x, if the function is getting smaller and smaller values, then it's a decreasing function. We talked about that. Okay, how about this? Is this an increasing function or decreasing function? This function, this is an integer ceiling function. Let's look at greatest. Don't confuse you with integer ceiling. Forget that. Just look at greatest integer. We are going to just focus on this. One is enough. Okay, let me close that. Is this an increasing function, decreasing function, or none? What do you think?
Increasing.
Sometimes it becomes constant, right? So for example, if you start at -2, it is constant first, between -2 and 1, then it increases. And between -1 and 0, it is a constant function, then it increases to this point. And then at 0, it is a constant till 1, and then it jumps up. Okay? So in other words, on the intervals like 0 to 1, 1 to 2, 2 to 3, etc., it's a constant function, but at the endpoints, the natural numbers, integers 1, 2, 3, 4, it just jumps up. Okay, actually, overall, it's an increasing function. Okay, it's a non-decreasing function. We call it non-decreasing. Okay, non-decreasing means it's gonna either, sometimes it's gonna be constant, sometimes it's gonna be increasing. Okay, it's not constantly increasing. It's a non-decreasing function. It doesn't decrease. It's going to increase, but it's going to just sometimes stop, okay, rest a little bit, become constant, and then jump up and continue, blah, blah. But it increases overall, okay? We call it non-decreasing function. Okay, let me write it here, okay? Indeed. Okay, let me make it bigger for you to see. Okay, let's arrange the size as well. Okay, this function, okay, okay. This function is a non-decreasing. So it doesn't decrease. It's gonna either increase or it's gonna become constant. Sometimes it's a non-decreasing function. All right. We have a version of non-increasing function as well, but I don't have the picture right now, so I'm not gonna. Okay. Okay. So this function is a non-decreasing function. What does it mean? This means it's either increases or become constant. Either increases or become constant. Okay? Increases or become constant. All right? Okay. All right. So I hope this is clear for you. Let's go back to our functions. Okay. We talked about this. We We talked about this being increasing first and decreasing later. We talked about it. Do we have any interesting example up here? No. Okay, that's fine. All right. All right, so let's move on. This is the part that we didn't discuss with you. Okay, so we are talking about functions being symmetric with respect to the y-axis or the origin. So when you look at a graph, sometimes functions are symmetric with respect to the y-axis. So this is a good property, this is a good feature. And sometimes they are not. And we want to differentiate them. We want to give names to them. And actually, function being even and odd, you can actually, this is going to differentiate functions being, having the graph symmetric with respect to the y-axis or not. For example, even functions are the ones that have the graph symmetric with respect to the y-axis. What does it mean? It means just this, look. Is this function symmetric with respect to the y-axis? Can I get a response? Yes.
Yes.
And therefore, we are going to call this function as an even function. Okay. So we are going to say this function is an even function. But there is another, let me open this up, make it bigger for you. Okay. I'm going to move a little bit here so that I have more room to write. Okay. All right. So enlarge the size of my writing. Okay, so we are gonna say y is equal to absolute value of x. Absolute value of x. Where is x? Is symmetric. The graph of this. All right, the graph of y is equal to x is symmetric with respect to. This is the abbreviation for with respect to. Okay, you understand? With respect to the y-axis. All right, it's the y-axis. It's symmetric with respect to the y-axis. Therefore, it is called an even function. It is called an even function. Okay. Do you know any other examples of an even function that we learned?
Parabola.
Parabola is an. That's right. Perfect. Okay. Moreover, okay. y is equal to x squared is also even, okay. But there is a formulation that's going to tell us that these are even. Okay, the formulation, because in math it's not only enough to say, oh, pictorially this is like this is even because it's symmetric. It's not enough. We want to express everything in terms of what? Functions. We want to express everything in terms of equations. We want to just write everything in terms of math language. Okay, so therefore, actually this even function, there's a definition. F of negative x is equal to f of x. So if you have, sorry about that. Okay, if you have this property, okay, this is the mathematical formulation of even function. Okay, this would mean that it is even function. Okay, if a function satisfies this, then it's an even function. Let's check it. Okay, let's check this. Let's check this formula. Check this definition. Okay, how would you check this for this absolute value? Let's check. I'm gonna write f of negative x, which is, let me write that here. I'm gonna copy this here. Okay, I want it below though. Okay, I'm gonna erase it. What is f? F is, let's check for, okay, let me do this. Okay, example for you to understand. Let's check. Okay, let's check this definition for y is equal to absolute value of x. Okay, we are going to take that. So we are, f of negative x is what? F of negative x is negative x, right? Because I just, instead of this, I put just negative x in there. But I know the absolute value of negative x is what? Do you know, guys? What is this equal to? Is it true? Is this equal to this? Do you agree with that? Yes or no?
Yes.
Yes.
Yes, definitely. But this is the same as this, right? So did I show that f of negative x is equal to f of x? Did I show that? Yes, I did. So this is going to tell me that this proves that absolute value function is an even function. Okay? So why do we need this actually formulation? Because sometimes some functions are going to be even functions, but we would, okay, or sometimes I would ask you to check a function is even, but you wouldn't have the graph in front of you because it would be a complicated function. And then you would just use this formulation to check it out, okay? So another example I'm going to give you, this y is equal to x squared is also like that. Okay, let's check. All right, I'm going to copy that here, and I'm going to just modify. Look, let's check that f is equal to absolute value of x squared. Let's check the definition for x squared. Let me enlarge this. Okay, I have to move it up. Oh my God, it doesn't come up. Okay, maybe towards right. I'm going to move towards right. Okay. Maybe I have more room that way. Just one sec. I have another urgent call from the university. I'm so sorry about that. Okay. I need this is coming from the rector's office, so I have to take like 5 minutes off. I need to talk to them. I'm so sorry about that. Let me think about this example for yx squared and try it out at home on a piece of paper and show that this x squared is also an even function. Okay, I'll be back in 5 minutes. That's what they say. Okay. Or we could do, actually, we can take our 10 minutes break early. Okay, let's take our 10 minutes early. So let's meet at 9:52. How is that? Okay, let's do that. Thank you very much for your understanding.
No problem, teacher.
Thank you.
We can leave?
You just stay here. I mean, you
Okay,
can take a break, but you can stay here. Okay, thank you.
See you.
Bye-bye. Hello, everyone. I think I said 54. Did I say 54? I think break is over, right? Is that right?
Yes,
Yes,
break is
teacher.
break.
Okay. Mhm. Okay, I'm done with my talking over the phone. I'm going to, excuse me. I'm going to start. Okay, we were discussing about even functions, right? For even functions, what's an even function? First of all, the graph is symmetric with respect to the y-axis. And what are the examples? Absolute value of x is an example, x squared is an example. Okay, we have two examples here, and actually we showed there's a formulation for the even functions. Let me make it a little bit bigger as well. Okay. All right. So, right, let me make it. Let me make it nicer here. Okay. All right. So then next we are gonna check y is equal to x squared is an even function. How do we check that? It's the same rule. Look, I'm gonna erase this part. Instead, I'm gonna write. I'm sorry. Let me make it negative x squared. Right? Where's my squared? Okay. And then instead of absolute value of y, okay. Let me erase that as well. Okay. So what is the square of negative x squared? Square of a negative number is positive, right? So this is going to give me directly x squared. But what is x squared? It's my original function, which is f of x, right? So this proves, actually, I showed, okay, let me write that too. I showed this, let's see. I showed that, okay. I showed this is equal to that. Okay, I showed that f of negative x is equal to f of x. And this is going to prove to me that not the absolute value, the parabola, which is y is equal to x squared, is an even function. Okay? Okay. But, okay, and not every parabola is an even function, right? Okay, note. Not every parabola is an even function, right? Is an even function. Why not? Okay, for example, you remember the example we gave? Y is equal to let's see, x minus 2, okay, squared, right? I mean squared. I mean, just a sec, squared, yeah? This is a parabola as well, but this is not an even function because this is a shifted function towards left of the graph of y is equal to x squared. If you shift it by 2 towards left, it is not symmetric anymore. It's not symmetric with respect to the y anymore, right? Is not, okay, is not an even function. Is not an even function. So you do not want to generalize it, okay? You want to check whether we have this f of negative x equals to f of x property hold, okay? So that's it. Do you have any questions? I'm going to close this. Okay, so how about odd function? Odd function is a function that's symmetric with respect to the origin, okay? And it has this property, f of negative x is equal to negative f of x. If your function satisfies that, it's an odd function. What type of examples do we have? Let me open this up. Let's see what I had written here. Okay. Right. I had written here that, let's make it bigger for you to see. Even functions are symmetric with respect to the y-axis, and they satisfy f of negative x is equal to f of x. On the other hand, odd functions are symmetric with respect to the origin. Let me write this one. Notes. Okay. 1 and then 2. This is the second note. Odd functions are symmetric with respect to the origin, and they satisfy this property, okay? So what are the examples for the even function? Examples are, okay, absolute value function, absolute value function, and okay, and parabola that passes through the origin, right? I mean the y is equal to x squared, I mean. For this one, on the other hand, the example is this. Look. Okay, this is the example. Let's go back to y is equal to x cubed and see what type of a function is this. This is one of the functions that I want you to know very well, okay? So this one is an even function. It's symmetric with respect to the y-axis, but y is equal to x cubed is symmetric with respect to the origin. Symmetric, look at this line. If you consider the origin, this point is the symmetric of this point, okay? If you choose this point is symmetric with respect to this point. So it is symmetric with respect to the origin, okay? So the, what have we written here? Let's see. All right. Okay. Okay, y is equal to x cubed is an odd function. Why? Okay, this is the example. Okay, let's check it out. Okay, let's check. Let's check it. Okay, how would you check? I have the formulation f of negative x is equal to negative x cubed, which is equal to negative x cubed. That's true because if you take the negative third power of a negative number, it's negative again. All right. So to make it clear, it is the same as like this. Okay. But what is x cubed? It is f. So we got that. Okay. This is nothing but okay negative. I'm going to just copy from here. Okay. So we got. All right. So we got that f of negative x is equal to negative f of x. This would imply that this function is an odd function. Okay, that's how we get it. Okay, so even and odd functions are like that. Any questions? Okay, these graphs x squared plus 1, x squared, these are symmetric with respect to the origin. They are even functions. Y is equal to x is an odd function. Excuse me. And then y is equal to x plus 1 is neither odd nor even. So sometimes, okay, let's write a comment here. All right. Okay, example, y is equal to x plus 1, okay, is neither odd nor even. Sometimes functions are like that because it's not going to satisfy, it's not symmetric with respect to the y-axis, it's not symmetric with respect to the origin. You can check it, check the formulas, okay, check the formulas to see, okay, so proof, for example, y is equal to negative x plus 1 is not the same as, is not equal to, okay, y is equal to x plus 1, yeah? I put negative x for x, they are not equal, so this shows it's not even. This shows that f is not even, okay? And also let's check something else. Okay, second thing is this is f of negative x, to make it clear for you. Okay, this is it. Okay, and this is f of x. Okay, and okay, I'm gonna put negative of x and minus this and this. Okay, do you see that? So this is f of negative x, which is negative x plus 1, and negative f of x is negative x plus 1. Are they the same? Are these two the same? F is not odd, we should say. F is not odd. Okay? Do you understand? Did you get it? Let me get some comments from you. Did you understand?
Yes.
Yes.
Okay, is it clear? Okay,
Yes.
okay. Thank you. All right, so I'm going to close that. So we have seen examples of even functions, odd functions, neither odd nor even function, okay? So we got all that. All right, so these are about lines, and the lines have positive slopes. If you like, 1/2 is a positive slope, 1, 2, etc. And these are the negative slopes. So if you have a negative slope, the line is gonna be looking like that. This is a constant function, and the slope is 3/2. These are just these are the things that you already know. Okay, let me see. Actually, I want you to be aware of this. Okay, let me make it a little bit bigger for you. Okay, so these are our popular functions. Okay, so note, make sure that you know these graphs. Okay. Okay, make sure that you know these functions and their graphs. Their graphs by heart. Okay, that's what we expect. Okay, these functions. What are these functions? Y is equal to x, just a line. Y is equal to x squared. Y is equal to x cubed. Y is equal to x to the 4. Y is equal to x to the 4 is also symmetric with respect to the y-axis. Y is equal to x cubed is symmetric with respect to the z origin. So this is an odd function. This is an even function. Odd function, even function, and odd function. Okay, so depending on the power of x, it's going to be 1 even, 1 odd, 1 even, 1 odd, right? F of x is equal to x to the n. Okay, for even powers, it's going to be even function. For odd powers, it's going to be odd function. So I want to give you another example here. Example. Okay, check whether the function f is, just a sec, function f of x is even or odd or neither. Is even or odd or neither. Okay, what's the function I'm going to give you? F of x is equal to x to the 4, x to the 6. X to the 6 plus x to x cubed. Okay, is this even or odd? What do you think? Plus, let's say 30, okay, or 39. Is this even or odd?
None of them.
It is neither. Okay, answer. It is neither. It is neither. Okay, we have this even power here. This is even, but this is an odd function. If you add even and odd, you're gonna get neither. Or right? Okay, easy. You can use the formulas and show that. Okay, I'm gonna skip that. Okay, so next we want to talk about, these are also our well-known functions. Y is equal to 1/x. We talked about this before, the domain, etc. And we talked about where they go to as x approaches. I think we did with you. Let me read this as a reminder, because these are important features. We are going to come back to it, but you need to. Okay, we call this butterfly function. We talked about the butterfly function. Yes, did we?
No.
No? Okay, y is equal to 1/x. We are going to make use of it a lot. So keep this in mind. This is one of the functions, my favorite functions. Okay, y is equal to 1/x, and it's called butterfly function. And I told before, maybe in this class or other class, one of my students gave this name, butterfly function. It is like a butterfly, right? Do you agree with that?
Yes.
Yes, it's like a butterfly. So, and the domain is everything except all reals except 0. So, which you can write like negative infinity to 0, union 0 to plus infinity. You can write it like this. And then the range is the same as the domain, because the 0 is not included. Why the domain doesn't have 0? Because 1 over 0 is undefined. And why the range doesn't have 0 in it? Because there is no x value that you can put in that's going to give you 0. Okay? So therefore, domain and range are the same. They don't have 0 in it. Okay, let's get some, I have some notes here that's listed. So in we need to know, so in this class, we need to know the behavior of the function, because as future engineers, you will be working, okay, so what you're going to do, you're going to be given a real life problem, and then you're going to translate that real life problem to, you're going to express them in terms of mathematical terms, and you're going to create a mathematical model of that, okay? So when you're doing it, you're going to use functions. So you need to know functions very well, okay? How they behave. So in this class, we are going to be learning the behavior of the functions. So what is the behavior of this function as in its interesting points? For example, 0 is an interesting point. What is the behavior of the function near 0? So if we approach the 0 from the right, points like that, 0.9, 0.001, 0.000005, okay? So as you get close to 0 from the right, how does the graph behaves? We just look at the graph gets bigger and bigger. Look, the values are getting bigger and bigger. So we are gonna say, as we approach 0, as we get close to 0 from the right, the graph is taking very large values, so it's going to go to plus infinity. And then let's look at, so we are interested in behavior of this butterfly function as x approaches to 0 from the left. How does it behave? For example, approach to 0 with the points -1, and then -0.5, -0.002, -0.0000005, okay? You get closer and closer to 0 by taking values like that. And then how does this graph behave? This graph gets very small. The values are getting very small. Do you see that? It is all negative and getting very, very small. So this will tell us that as we get close to 0 from the left, the graph is going to approach to negative infinity. All right, so what happens when x approaches to plus infinity from the right? As x gets bigger and bigger, where does this graph gets close to? This graph gets close to 0. Do you see that, right? But never touches 0, never ever. And let's look at the behavior of this graph, this function, as x approaches to negative values to the left, on the left. As these x values getting smaller and smaller towards left, how does the graph behave? Graph gets very close to 0 again. Okay, so these are important features for this graphs. When you are talking about a function, you should look at the graph and especially check out these type of points that are special. In this case, 0 is a special point. Infinities are special. Okay, so check it out how this graph is behaving when you get close to these numbers. All right, and we write them all here. As x gets bigger positively, then y gets close to 0. As x gets smaller negatively, then y gets close to 0 again. Okay, as x gets close to 0 from the right, which means with positive values of 0, close to 0, then y gets very, very large. It will approach to infinity. And then last thing is, as x gets close to, I can't see it, just a sec. And you wouldn't see it either. As x gets close to 0 from the left, taking negative values, then y gets very, very small. It will approach to negative infinity. So this is the behavior of the button.
Teacher, we can't hear you, or I am the only one to have that problem.
No, we
No,
cannot.
we can't. We can't.
Okay. Çıktı hoca.
Düşmüş de olabilir.
Büyük ihtimalle
düştü
düştü
ya.
zaten çünkü interneti gittiydi ya zaten duyamadıydık.
Aynen. Kesilip duruyor.
Okay, which part by the way? Which part
Actually,
you gonna do?
Like the 30 seconds.
yes. And your screen isn't on our screen too.
Okay, so I have to thank you for that. Thank you for letting me know that. I'm gonna do that right away. Sometimes
Okay.
it just goes like that. So I can't stop it. Maybe Teams is tired sometimes. Gets tired. Okay. All right. So if this happens, let me know. Okay. So did you hear what I said about the 1 over x? This 1, 2, 3, 4. Did you hear that?
Yes.
Okay,
Yes,
okay.
we heard
Yes.
that.
Perfect. Okay, next, my favorite function. These are the functions that you are going to use whole first semester and second semester, so you should keep these in mind. These are favorite functions that are used quite often. It's not only my favorite, it's everybody's favorite functions, okay? Even your physics teacher's favorite, okay? Because these are used a lot. Common functions, okay. All right, so let's see. So y is equal to 1 over x squared. So this is again, first of all, when you look at this, is it an even function?
Yes.
Definitely, it's symmetric with respect to the y-axis, so it's this even function, perfect. And then what else can we say? What's the domain? It is written here, right? The domain is x cannot be 0 because it's the denominator can never be 0. How about the range? Since we have x squared, you cannot have negative values in the image. Do you agree? Yes.
Yes.
Okay. And 0 cannot be in the image like 1 over x as well. Okay, can you find a name for this function graph? Can anyone be creative and find a name, informal name?
Volcano.
Oh, volcano, that's nice. I love that. Okay, this is called, okay, perfect. This is called a volcano function. Perfect, I love that. Okay, this volcano function, okay, we know the domain is written here, blah, blah. We need to know how this behaves at the special points. For example, at the origin, okay? So behavior of the function, behavior of the function. Okay, what's the behavior of the function? One. First of all, if you approach 0 from the right, as x gets close to 0 from the right. Okay, from the right. How many minutes do we have, by the way? We still have a lot of minutes, right? 10:50, we have like 30 minutes. More than 30 minutes, yeah, that's good. Because I like talking, so I don't want to just go over our time. As x gets close to 0 from the right, okay, positively, yeah, right? I mean positive values, okay, positive values, such as 0.001, okay? What happens to f of x, okay, gets very large, all right? And they go to, I mean, it goes to infinity, plus infinity, all right? So I'm hoping that everybody sees what I'm saying. Okay, so let's write the second behavior. I mean, the behavior close to 0 from the left. I mean, behavior number 2. It's special points. As x gets close to 0 from the left this time, left with negative values, okay. F of x gets very large again. It goes to plus infinity, thank God. Okay, let's write another behavior number 3. As x gets close to plus infinity, I mean, as x gets very large, okay, taking positive values, f of x gets very small. Okay, very small. Okay, very small. Indeed, it goes to 0. Okay, it gets close to 0. It is never 0 though. It is It is never ever. It is never. It is never 0. Okay. How about if x gets very small? Okay. Or you can say if x gets very large, negative values. Okay. You can also say that. Very large, we mean the negative values. But negative values, I mean, of course, the values are not getting large. Let's write it gets very small, not to confuse you, okay? Sometimes this is used as well. Gets very small, I mean negative values. F of x gets very small again, it goes to 0, and it is never ever 0. Okay, this is the behavior of this volcano function. Who said volcano? Can you tell me your name?
I'm Aysu.
Aysu?
Aysu Deniz.
Aysu Deniz. Okay, thank you, Aysu. All right. So I'm going to mention your name in other classes, by the way. Okay. All right. So let's move on. Okay, what is this? I think there's some pages are missing because there's a typo. Ignore this written here. Graphs of power functions. This is not related to this. Okay, this is a typo here. So the things that is written next to 116, figure 116, it's not belonging to this picture. Okay. All right. So, and we talked about this interesting curve before, right? This is also favorite. Okay, we will be able to create other functions by using this favorite function as well. All right, so we talked about the domain of that. And see, can anyone find a name for this? I couldn't.
Throwing, maybe.
Say it again.
Throwing something like that.
Okay, throwing function. Okay. Any other suggestions? It's not a wave. I just
It could be a fishing rod stick.
A fishing?
Rod stick, I think that's what's called.
Fishing
Wait a minute.
Rod?
Wait a minute, please.
Can you write?
Okay.
Fishing rod?
Fishing rod, yes, it's fishing rod. It looks like a fishing rod.
Yeah, you are fishing, right? You are fishing from the right though, right?
Yes.
Okay, that's it. What's your name?
Emir Gümüşbaş, teacher.
Emir, okay, thank you. Okay, fishing rod function. We have this fishing rod function. It's like you are fishing. And this is also a favorite function. All right. So we have this domain as such as 0 to infinity, and the image is 0 to infinity, etc. Is it even? Not at all. Is it odd? Is this odd? Not at all, because there's nothing towards left. It's not symmetric with respect to origin, neither even nor odd. Okay, and let me see what and then this is also a favorite, but not as favorite as the others, okay? This is x to the 1/3, okay? This is x to the 1/3, and these are x to 3/2. You should know that we have these guys as well, okay? We are not going to name them, okay? But this is similar to, remember, the second one is like y is equal to x to the 1/3 is similar to, the graph is like similar to x cubed, but x cubed is going up, right? Up like this, concave up we will call later on, and concave down here, and this is concave down here and concave up here, okay? We are going to talk about this terminology soon. So, all right, so, but this is, the second one is odd function, is it? Y is equal to x to the 1/3. This is an odd function, right? Isn't it? Yes, it is. Okay, let's write that. Where is it? Okay, this is an odd function. You all agree, isn't it? Because it's symmetric with respect to the origin, like x cubed. Okay. All right, so let me put. Okay, let's put this close to that. Okay. Okay. And later on, we are going to talk about these two guys, okay? Especially this function has an interesting behavior at the origin. Do you see that? It's like V-shaped, but curved V-shaped. Okay, let's write it that too, because we will talk about this in the future. Okay, this graph, this function is even function, isn't it? Is it even?
Yes, it's even.
Is even, okay, and it's at the origin. It has its interesting and extraordinary behavior. At the origin, it behaves. It behaves almost like a V-shaped, almost like absolute value, but it's in a curved way, in a curved V-shaped, right? It's not the V-shaped like the straight V-shaped, it's a curved V-shaped, okay? So this is an interesting behavior at 02. We will talk about it in the future, okay? When we are learning some other stuff. That's why I put it in here, okay? All right, so let's put it next to it so that it belongs to that. And I'm gonna put my thing in here. All right, that's good enough. So you understand that in this class, you should get familiar with the functions. And let me close these guys. And I want you to look at this definition. Okay, graphs of power functions. F of x is equal to x to the a is equal to 1/2, 1/3, 3/2, 2/3. Now, why do we have this page? We have this page because this page is talking about a power function. Power function is a function when you have x to the something, x to the k, and k can be any value, okay? So these are the examples of that, power functions. This is the terminology that you would hear, okay, because it's the power, it's in the power. Okay, then we have some other graphs like polynomials, all right? Okay. Polynomials, I didn't talk to you about. Polynomials are, you can consider them as a combination of powers of x, but the integer powers. It's not just power functions, okay? So for example, x cubed, this is integer power, okay? So these type of things are called as polynomials, and you have heard of it in high school, I believe. And the graphs are weird, look, they are all curved like that. And at some parts they are increasing, decreasing, and you will see that we will deal with the polynomials are the nicest, one of the nicest functions you can ever see, okay? We are going to make use of them a lot. All right, nice, I mean, I told you that they are nice because later on we are going to learn about differentiation, integration, and these functions are nice, continuity, continuous functions, we will talk about that. And these polynomials are nice in a way that they are continuous functions, they are differentiable functions, they are integrable, you can integrate them. So they are all good. They're all good. But later on, you're going to see some functions that are not differentiable, that are not continuous, that are not integrable. You cannot integrate them, okay? So polynomials are really good. We love them because they are easy to deal with. Okay, and then there's a new terminology which we call rational functions. Okay, let me write it down here. Okay, so that you know the terminology that we are interested here. Okay, what is a rational function? I will tell you. Okay, let me see. Okay, rational function. This is important. Okay, what's a rational function? Let me tell you. Rational function is a function f, okay, f of x, where it is the ratio of two polynomials, okay, polynomial over polynomial, polynomial over polynomial. But we want to write, this is not a good writing, we want to write it in math, okay? In mathematics, you can write this as follows. Look, you can write this polynomial over polynomial like that. P of x over I mean, over q of x. What did I do? Okay, sorry. Okay, where p and q are polynomials. Where, let me write here, p and q are polynomials. Polynomials, okay? It's just ratio of the two polynomials. We call it rational function. We use it a lot. Look at the first example. It is 2x cubed minus 3. It's a polynomial. Over 7x plus 4, it's a polynomial. Polynomial over polynomial. Look at the graphs of those. We have some red lines here, okay? These red lines are called, what do we call it? Anybody knows? Okay. In the graphs, you would see red lines. Anybody knows what these red lines are? Anybody knows in Turkish?
Asymptotes.
Yes, are called asymptotes. Okay, let me write it in big. Okay, these are called asymptotes. And we have, what type of asymptotes do we have? Look, sometimes we have vertical asymptotes, sometimes we have oblique asymptote, which we say it's just a regular line like this. Just one sec, I need an interruption here. Give me one sec. Give me 1 minute, okay? Okay, I'm back with you. I'm sorry about that. All right, so we were talking about asymptotes. There are a couple of versions. I have a vertical asymptote, I have a horizontal asymptote, I have an oblique asymptote, which is like this line, okay? So this is a horizontal asymptote. This is a vertical asymptote, okay? Let me write these names down because we are going to get to them, okay? Types of asymptotes. We are going to get into the details later on, okay? Not today. But I'm writing these here so that you are opening some page in your heads, in your brain, that we will discuss them in the future, okay? This is just for future work. Okay, vertical asymptote. Okay, horizontal asymptotes. And then oblique asymptotes. Okay. Okay, so it's good that you see these names ahead of time. Then in the future, it's going to be easier to consume, or it's going to be easier to understand the details of that, okay? So this is our summary for this part. Okay, so these are called rational functions, and in rational functions, we should expect that we have asymptotes in the graphs. And then because of the, why do we have the asymptotes, by the way? Any ideas? I mean, where do these asymptotes come from? Any suggestions, any guesses?
This is the first time I heard it.
Okay, great. What's your name?
Ahmet.
Okay, Ahmet, Kendirli, right? Okay.
Yes.
Yeah, Ahmet, look, this is a polynomial over polynomial, right? If you look at the denominator becomes 0 at a point. Do you see that? For example, here it is 0 at -4/7. Do you agree?
Yeah.
Okay, those points are the points where we have the vertical asymptote. -4/7, x is equal to -4/7 is a bad point because it makes the denominator 0. So the bad points are going to give you asymptotes. So x is equal to -4/7. It's a line, it's a vertical line, and it is this red line. X is equal to -4/7. So that's where we get the asymptotes. Asymptotes are the lines that our graph cannot, cannot easily pass through. Like we are going to get very close to them, but most of the time they are not going to pass. In the second example we have, the graph passes, but as x gets bigger, I shouldn't say it doesn't, I mean, we are going to have vertical asymptotes where the rational function are going to have zeros when you plug in. Okay? But
Teacher?
the oblique and vertical, horizontal, we will discuss it separately. It's different.
Can we consider it as a limit of the polynomial, the asymptotes?
If you take the limit of this, yeah, we are going to do that. It's going to be the case when we for the horizontal asymptote. And for the horizontal, we're going to take the limit. Look, you're right. Look at the b. In b, we are going to take the limit of this function as x approaches to infinity. And then the limit is going to be 5/3. Look, the horizontal asymptote is actually 5/3. Y is equal to 5/3. You're right. We are going to get into these details in close future. I mean, okay? We are going to get to them. Yeah, what you're saying is right. Okay, and also oblique is going to be defined by dividing this polynomial by that. You're going to get, you're going to do the long division, and you're going to get a line equation, and this is a graph. So we'll talk about this in the future. I'm just telling you right now so that you are getting familiar with that. Let's see. Okay, so we have algebraic functions as well. Algebraic functions are the ones that are not polynomials. Okay, you're gonna have like power functions in it like this, 2/3. So functions that are not polynomials, roughly you can consider as algebraic functions. Okay, so I'm gonna get to the next one. So we have these famous functions as well. In electrical engineering, they are going to use it a lot. Trigonometric functions, right? The very famous of the two is sin x and sin x. And sin x, these are the wave functions, right? You can consider them wave functions, maybe. Let's give them names. Okay, they have already names, trigonometric functions. But we see the waves here, okay? You can just remember them like waves, okay? Especially cosine and sine. And I want to just write a couple of things here. Y is equal to sin x, okay, is a shifted graph of what? Of what do you think? Shifted graph of which graph?
Cosinus?
That's right. It's a shifted graph of cosine x. By how many units and towards where?
to the left.
You want to shift cosine x to the left or to the right?
No, I want to shift the sine x to the left to get the cosinus x.
But I'm saying sine x is a shifted graph of, I want to shift cosine. Where should I shift?
Right.
To the right.
To the right. By how many units?
90 degrees.
By 90 degrees, or pi over 2. We use radians here, right?
Yes.
Pi over 2 units. Okay, pi over 2 units to the right. Let's check. So let's move this cosine to the right by pi over 2, and you get the cosine. And you can say a similar thing for cosine. So let's write that. Okay. I'm going to copy this down. Let me make it bigger, sorry. Okay, this is 1. Okay, this is 2. Y is equal to cosine x. Cosine x is a shifted graph of y is equal to sine x. Towards where? To the right or left? Do you want to see?
This is left.
So we want to shift sine x now. We shift the sine x to the left. It should be to the left then, right? Isn't it? You are going backwards. By pi over 2 units. Okay, perfect. Perfect. And then these functions actually have periods. Okay. Okay. So what does it mean, a period? Let's recall that. I want you to look at sine x only. And then I want you to look at sine x on the interval 0 to 2 pi. Just look at that piece, 0 to 2 pi. And we are going to call this one wave. Okay, okay, consider. So I'm going to give you a definition now. Okay, okay. Okay, what's the one wave? One wave. Okay, one wave is, okay, y is equal to sine x. It is the part of sine x graph on the interval where, I mean, I'm writing, it is part of sine x on the graph, on the interval, I'm sorry, let me erase this, on the interval 0 to 2 pi. I want you to focus on that. 2 pi, all right, 2 pi. Let me write this pi small. Okay, 2 times pi. Okay, and this is included. Okay, so I want you to look at this one wave. Okay, one wave. Let's look at that here. So this is our one wave. Okay, actually, can you consider sine x as produced by repeating this one wave to the right and to the left infinitely many times? Can you see that? Can you understand what I'm saying?
Yes.
Indeed, you can produce sine x by, okay, by moving one wave, okay, you can create, I should say create, okay, by moving one wave to the right and to the left, to the right and to the left, infinitely many times, infinitely many times, right? You create this sine x like that. So this one wave is special. Actually, this one wave comes from, and we the terminology period, we call it a period. Let me write it big. Okay, so because of this period of sine x is 2 pi. Okay? All right. And similarly, I want you to look at, okay, this is, we have similar thing is same for the cosine as well. Let me enlarge my, or maybe I should just divide it into two. Let me write another note here, because otherwise I'm going to get into trouble. Just a sec. Okay, Control C. I'm going to have another note here. Commands. This is for cosine. All right. And I'm going to copy this down, and I'm going to expand it. And I'm going to write this for cosine. Okay. Okay, Control X and go up. Okay, so in this case, y is equal to cosine x is a shifted graph of y is equal to sine x to the left, blah, blah. One wave for the cosine, it is the part, let's see one wave, what one wave is. We are going to take the one wave from 0 to 2 pi again. It is this one, okay? One wave for cosine is the part of cosine x, all right? Cosine x graph on the interval 0 to 2 pi, okay? Indeed, you can create cosine x graph, okay, by moving one wave to the right and to the left infinitely many times. And because of that, we call it period, and the period of cosine x is what? Is 2 pi again, okay? Does that make sense? Let me correct this too for you. Okay, all right. All right, we got that too. Okay, I want to do something here. Maybe, okay, I want to give you an example. Okay, draw the graph of y is equal to sine x plus 5. How would you draw the graph of this? Can you say? Can anyone say? How should we think about that? Can anyone say?
It is the graphic of sinus x to the shifted 5 units to the left.
Perfect, perfect. Okay, it is the graph, it is the shifted graph of y is equal to sine x, next, to the left by 5 units. Okay, you can very easily, you can actually do it on your notebooks right now. I cannot draw it here, but just draw it and see. Can you draw it and see, please? On your piece of paper, can you draw it? And can you show? Can you draw sine x plus 5 and show it to me on your pages? Like, open up your video, and I want to see that.
Sorry. We shift the graph of y sine x to the left by 5 units of what?
5 units.
5 p's.
5 units. You're gonna count 5. 1, 2, 3, 4, 5. 5 units. You're gonna just shift it towards left.
Okay. Okay.
Is this clear? Who's talking?
I'm Ahmed.
Ahmed?
Yeah.
Ahmed, did you understand? Can anyone try to draw it and show it to me on the screen?
Teacher, I'm showing it, but I'm not sure if you are seeing it.
Anyone show? Okay, yes, let me see it. Can you move up a little bit? Okay, you shift it towards, this is the sign, towards left, right? Okay,
Yes.
perfect. 5 units here. Perfect. Thank you very much. For Emir, right? Okay. Thank you, Emir.
Yes.
You're shifting towards left. Yeah. You should practice this.
Teacher, you are muted. We can't hear you.
Okay. Sorry about that. You have to shift it towards, I forgot. You should do it at home, shifting to the right, to the left. And we have shifting up and down as well. Let me show you that too, okay? Shifting up and down. So I'm gonna give you another example. Okay, now, Control C, I want to draw the graph of y, x plus, not plus, sorry, x plus, let's see, 10, okay? Sine x plus 10. So what type of a graph do you think? So how can we draw this graph? In this case, I'm adding 10 to sine x, not to x. Can anyone tell me how to do that?
We should get it up like 10 times.
Okay, that's right.
In
That's
the-
right. In the which direction? You're
Like
towards
not
up, right?
X,
Upwards again.
upper direction, yeah.
Yes, perfect. Just give me 1 sec, okay? I need to take a couple of seconds. Can anyone draw the picture and show me, please? Okay, so it's gonna be nobody showed. Can anyone show picture because it's last couple of minutes? A couple of minutes, and so it is gonna be the shifted graph of y is equal to sine x up. Okay, up by units, by 5 units. Okay, that's how we are gonna do, and okay, so we are gonna draw the graph in the next class. Class is over. Thank you very much for coming, and I want you to say bye in here. Thank you.
Okay, teacher. Thank you too.
Take care. Bye bye.
good
See
day.
you next time.
See you next.
You too. Bye bye. Enjoy.
Hocam, can I ask a question? Simel hocam, can I ask a question?
Go ahead.
Why it goes 5 plus 5? Why it is not plus 10 to y exim?
Ha, Süleyman, Türkçe söyleyebilirsin. Hangi örnekle
Tamam.
ilgiliydi bu?
Son anlattığınızda dedik ya sin x artı 10 dedik ya. Siz dediniz ki sadece 5 yukarı çıkar. Neden 10 değil?
Yok, yok.
Hani
Yok. Ha, bir bakalım, ben belki şeyde açalım onu bir dakika.
Tamam hocam.
Şimdi orada bir yanlış anlaşılma olmasın sakın. Ha, o ten olacak. Tabii değil. Evet, evet, o ten olacak. Özür dilerim.
Tamam.
O ten olacak.
Tamam.
Doğru, haklısınız Süleyman. İyi ki
Kafam
söylediniz.
karıştı.
Yok,
Bekledim, ben şey dedim. 5 aşağı 5 yukarı o da olmaz yani, öyle bir şey olmuyordu.
Evet,
Tamam.
evet. İyi ki söylediniz.
Teşekkür ederim.
Tamam. Çok teşekkürler.
Görüşürüz.
Görüşürüz. Bye bye.